Let's get started. Hi, I'm Ayush. I am a postdoc with Vincent and also with a couple of other profs with Bill Freeman and Josh Tenenbaum. Vincent is traveling, so he asked me to give this guest lecture on how to do research, which is a big task. Just as a disclaimer, I don't want to claim that I know exactly how to do the best research. So I'm just going to give some results from my research and the guidelines that have led me to get to those results. I do believe that the best research that I will do in life is ahead of me and not the research that I've already done. So there are some principles, guiding principles that guide me towards like how to find the right problems, how to do the right kind of research. Some of those guidelines are just things I found. Some of them are from Vincent, Philip, and other people who have done great research, and it's good to listen to them and think about how they think about research. The slides have been, I think these slides originated from Philip Isola in the computer vision class, and then Vincent adapted it, and then I adapted it. So it was really fun when I was making these slides to figure out like which thoughts came from Philip, which thoughts came from Vincent, and now you have to figure out which thoughts came from me, from Vincent, and from Philip. It's a fun game. I can stop and you can try to guess like which ones are, which ideas came from which person. Okay, let's get started. Here's a brief overview of the research that I do, which I think aligns very well with what you guys have been studying in this lecture. So I build systems that learn to understand and interact with the visual world. So given this single image, this image is a photo taken from a car in the south of France. Some person is driving there. I just took a snapshot from a video. And just on this one snapshot, like there's so many things going on. You can tell about what the different objects are in the scene, what are the different semantic instances. You can tell about the depth, so you have some kind of 2.5D perception. You know which objects are closer to you, which objects are further apart from you. You also have a lot of information on like true 3D, the things that are not really visible in the image. So if you take any of the cars, like if you take, I don't even know if you can see this, like this car, for example, you only see the back. But can you tell what the front of the car would look like, what the geometry would look like, what the appearance would look like? And I guess most of you will be able to do that for the truck on the back. Or even think about like what's going to happen. Like what do you think lies when you turn right? Like what's going to happen in the scene? We don't know exactly what's going to happen, but we can make pretty good guesses on what's going to be there in the scene. So we have built this mental model of the world that this image describes, and just from this single snapshot. And this single snapshot does not even have enough information for us to geometrically compute it, and still we build these rich mental models. So my goal is that I want to build computational models that solve the same task. So just from this single image, I also want to build these mental models that will eventually be useful for the same kind of intelligent tasks that humans do, for self-driving, for robotics, for computer graphics, and so on. Why is this problem challenging? It is very challenging, and that's why it's an interesting problem to study. So the first problem is the one I kind of alluded to, is ill-posed. So if you just have a single image and you're trying to compute the geometry of the scene, even ignore the occluded parts or the invisible parts, even for the visible parts, there's a lot of ambiguities. You don't actually know what exactly the depth of any particular point in this image is going to be. Mathematically, there are like infinitely possible 3D scenes that can project exactly to the same image. And we have to figure out what is the right, among all these possibilities, which ones are the plausible solutions. So this is the ill-posedness, so you need priors to solve this. And I guess you guys have already covered prior-based reconstructions, right? So that's this problem. Then there's uncertainty. This comes in place when you're trying to reason about things that are not directly visible. So again, like if you turn right, like you have to build a mental model of what's there when you turn right so that you can actually plan your actions about what you're going to do there. And there you have uncertainty. You don't exactly know what's going to happen, but you have some idea of what could happen. So you know that there's probably not a sea there, but you know that there's a street. What do the buildings look like? Are there people there? You have kind of plausible scenarios you can build up in the head. So there's uncertainty. There's not just a single solution. There's a set of plausible solutions. And finally, this is a point, I guess, which you guys have already covered, is the supervision. So we don't want to learn this from 3D data sets. We don't want to go out in the world and keep collecting more and more 3D data. We want to learn it in a self-supervised manner by just observing images and videos. And there are two reasons why you want to do this. One is that how do you even start capturing 3D data, right? Especially for large scenes like these, and for different tasks, and if you want to build a general system that can work in a different scenario. The second is, as humans, we didn't learn to perceive the world by looking at 3D scans. We learned by walking around the scenes and manipulating objects and playing with them. And we want the computer systems to also behave in a similar manner. Okay, so let's look at one of the results from my research. In this case, there's a single image that is the input to the system. And from there on, the method reconstructs 3D scenes that are consistent with this input image. The reconstructed 3D scene does not only describe the things that are visible, but it should also describe the things that could possibly lie beyond this particular part of the scene that this image captures, right? So you can reason about, if you had turned the camera, what would happen? It's the same problem as I described with the car. And in this case, it samples from the distribution of plausible scenes that are consistent with this particular image. Does that make sense? So you can do the same for objects, let's say. So if you see a hydrant like this, you could be certain about certain parts. From the back, it also has to look like a hydrant. But what does the texture look like? Do you really know? It's this kind of weird stochastic texture, pretty much. And this model can then sample from the distribution of the possible textures that could lie behind the object, behind the visible surface of the object. So this is one case where all those three challenges are met. It learns priors. So even from a single image, it can give you 3D. It learns about the uncertainty. It can tell you what are the plausible solutions. It does not just confidently give you one solution, which is a wrong solution. And third, it is self-supervised. So it does not require 3D scans. It just learns from videos. In this case, this was learned on a data set of real estate videos. So there are people, real estate agents on YouTube, just like showing around their houses they want to show. And from that kind of data, you can learn to do this kind of 3D reconstruction. Right? Feel free to interrupt me at any point. Yes? Yes, so you can do it autoregressively. So if you take this particular image and then you go to, let's say, this part of the scene, the space of ambiguity increases by a lot, right? So it always makes sense to move slowly so that the scenes are coherent, but then you can keep moving further and further in an autoregressive manner. In that case, it does work. So we have some examples where you can actually move out of the room, go into a corridor, move into another room, and stuff like that. But the modeling has some issues, and the more steps you take, the more errors you accumulate right now. That's still an open area of research. Okay. Then what is the structure of methods that are used to solve these kind of problems? The underlying concept is that I build generative models in 3D. So what are generative models? Generative models take as input some latent variables, usually from, the prior distribution that the latent variables are sampled from. Let's say it's a simple Gaussian. Those are the inputs to the model. And as outputs, you don't get the images, like for GANs or diffusion models that are very popular. What you get as output are the descriptions of the world, of the 3D world. It has all the structure that we want as outputs from our inference algorithms, right? So the generative models describes geometry, materials, lighting, objects, affordances, physics, everything we want to really reason about the world. Once we have built generative models like this, we'll learn inference methods that can take any single image, or even less information, like some very small amount of information, and then it looks at the generative model's latent space and tries to figure out what are the possible latent spaces that can explain this image. So there's a reasoning process going on, right? And this inference algorithm could be really anything. It could just be a deep learning forward pass. It could be just an optimization method. It could be a search algorithm. It could be MCMC. It could be anything. Once you have a latent space defined that gives you a distribution over plausible structures of the world, you can now search in that latent space and try to match which ones of these scene descriptions match this image. Does that make sense? Okay. And this kind of allows for two things. So two things we have, I think, answered with this kind of framework. One is the prior. Where does the prior come from? The generative model gives us the prior. Because we are searching in the latent space, it does not allow us to just like randomly give any random solution which is just not consistent. It will never give you a chair that is half bent when it should be rigid. That's the prior part. Where does the uncertainty aware component come from? That comes from the inference algorithm. So your inference algorithm, if it has the capability of sampling multiple different latent spaces that can explain this, so it could be as simple as you do a random initialization, and then you do an optimization from there, and you get two different positions. So if your inference algorithm can sample multiple points in the latent space, you can sample from the distribution of the ambiguity space, right? The third part is where does the supervision come from? And there it has to come from self-supervision. So you actually have to learn these models from the data that looks pretty much like images and videos. And this is kind of using the same kind of techniques that I think Vincent has been talking about in the class, using differentiable rendering and other techniques about what kind of scene representations you want to use, what kind of differentiable rendering methods you want to use that enables this kind of learning. So here's how I started working on this problem. So when I started doing my PhD within a couple of years, I had kind of already had this kind of a framework, and then I've been building upon it. So I started my research working on human faces, and this is one of the first models I built, where it learns a generative model over the geometry, reflectance, lighting, these kind of scene variables of human faces, and then it learns to do inference. So given an image or a video, it can now reconstruct what the geometry and reconstruction should be like. So in the middle, you see the geometry. On the right, you see all the components added together. You have the lighting and the appearance and the reflectance, just showing how well you can reconstruct any face. And the model is learned just from videos, like in most of the cases that you'll see here. Cool. Once I had the faces figured out, this method still required a lot of face-specific priors, and then the next goal was to make this more general. So then I moved on and tried to do general objects. In this case, we learned a model. These are samples from the generative model. In this case, you have the fixed geometry, and only the appearance is changing. So you can see that only the colors are changing. In this case, your appearance is fixed, and you're changing the geometry. And this is just the pose, so it's 3D, so you can sample from the distribution of pose. And this is learned from a data set of monocular images, so not even videos. You just have a random sample of a lot of images from each of these categories, and you can learn these kind of 3D models with semantically disentangled parameterization. And you can even do interesting tasks like correspondences. So you can draw a semantic mask on one of the images, and you can transfer this mask onto every other possible image. So this just goes on to show that with the right structure, with the right kind of inductive biases, you can actually learn a lot about the 3D structure of the world just by watching images, right? And then when I had the objects kind of figured out, I felt like I could understand how they work. I moved on to scenes, and that's the result I showed. So in this case, you can just take an image. I think this is one of the examples where you move out of a room, and then you go into another room. And there are a couple more like this. So you can just take any image. In the first case, you can take the image of a bedroom, and you can walk out. It can create you this kind of a door. So that's how I moved in the complexity of the problem statements in this area of research. Cool. Okay, so now with that background, let me tell you about how to do research. And it starts with why to do research. Any guess on who made this slide? It's Philip, yeah. Good. Okay. And how to do research starts with why you should do research. And I really like this slide when I read it because I agree with most of what is written here. So the first reason really is you can follow your own interest. When you start working on problems, you kind of develop intuitions and you have like ideas on like what you think is the right way of solving this problem. Or you have a problem that you feel like no one is really working on, and that seems to be a very interesting and left out area. You can actually follow your own interest. There's not really anyone who is forcing you to work on something. This especially holds true for professors, but also as a PhD student, you're supposed to gain independence, and this happens very early on. One example I think of right now is that in computer vision right now, especially in generative models, I think it's kind of very agreed upon that language helps a lot. So with the latest diffusion models or any other generative models, you would see that they're all language conditioned. And it is very obvious why language helps. Language is kind of like a very compressed kind of semantic representation of the world. So if you want to learn what cars are, well, why not use languages? It just makes sense. Why wouldn't you? But then there's the question of like, is language essential to learn vision? So language is something that happened very later on in the evolutionary process. You have insects that have vision, you have fish that have vision, birds solving incredibly challenging tasks without using at least as sophisticated languages we have that can represent all the cultural artifacts and everything. So it seems like there should be some computational process that should also enable vision without the use of language to the degree as the current methods do. But that might not be a viable thing to do in industry because you have language. Why wouldn't you use language, right? So I think that's something that I feel is my interest that probably I wouldn't be able to do anywhere if I was not actively working in open-ended research. Just an example. You can be creative, which is obviously one of the most fun parts and the challenging parts of doing research. And I think that relates very well to the next point, is that you can learn the scientific method. How do you find truth through hypothesizing, predicting, experimentation? If you haven't seen the Feynman videos and the other videos on the scientific method, you should watch it. It's like such a simple concept, and it helps you really formulate your problems and think about what you're really doing. And it goes on beyond science, of course. And I think the creativity here is involved in everything, but especially in the hypothesizing part. You can look at motion of planets, and you can come up with the theory of gravity. You can come up with the very basic laws of physics just by looking at data and having the right hypothesis. And that's a really creative process. Like how really do you move in the hypothesis space to get to the most general formulation to build a nice theory? The other point I think is the most the best part in practical terms, like discover something nobody knew before you. And for those of you who have actively participated in the research, you would probably understand how good it feels for that moment when you just like realize that, oh, I've just figured something and I'm pretty sure no one else knows about this. And this happened to me in the last project. I was working on something for around 6 months and it was just like not going anywhere. We were working incrementally on improving it and we just didn't know how to get it. And we had bits of pieces of like scattered information, and we knew that the mental framework is definitely not there. We don't understand the problem well. And then one day, it almost always happens out of sudden. One day you're just thinking about it and suddenly you just connect. You're like, oh, this is exactly how all these different theories or different problem formulations just fit in together. And now you've gone to an abstraction level where other people have not reached, and you can do something which no one else can. And that kind of moment is like kind of I feel this is the reason why you should work on research, because it really feels super good. The other thing is you can be bold. It kind of relates to the first idea as well. You can do things that other people might not think of or might not want to approach. And also, it's fundamentally entrepreneurial. You have high risk, you have high reward. And if you like being in that kind of spaces where you can really place bets, you can be creative and think about where you want to place bets on, this is something which really fits in well. Again, feel free to stop me anywhere. If you have ideas on what you think are better reasons to do research, or if you have better ideas to how to do research. Yes?
This is an idea. So a question about something you said earlier. It's a little bit tangential, but you said like one of the things you were wanted to do differently was you don't want to rely on language. So like more out of curiosity, like why do you think we shouldn't rely?
There are two reasons. One is intellectual curiosity. Nature seems to have computation. Nature seems to have shown us that there exists computation that does not rely on language and still enables perception, which is pretty good for solving intelligent tasks. If there exists a computation, can we figure out what that computation is? That's number one. It's like, it just makes sense, like it's intellectual curiosity. The other thing, I believe it also has a lot of practical benefit, because when you're using language and you're using it as almost as a crutch to solve vision, then you're most likely not using the visual data as well as you should be using. So it might be that the reasons why we don't see the language models, the visual language models to perform as well as humans might be because we haven't figured out how to extract that information from the visual data in the first place. So I think both of them are, in my opinion, valid reasons. Okay, then we move on to how do we recognize good research. And good research, this slide was already bold, the recognize and good part, and I think for good reasons, because there's a lot of research. So this NeurIPS, there are around 2,500, 2,700 accepted papers, out of which how many of them are good research? Maybe you can think about the slides and then go back and look, think about like in terms of percentage, like how many of the research that is actively being done at the forefront is really good research. There's a lot of noise in the process. And there's a lot of incremental stuff, which are papers that are not really solving important problems, or there's not much interesting ideas in them. So the goal is to do really good research that is impactful, that is interesting, that is novel. How do you define novelty? Any guesses on who made this slide? 3 options. No, it's Vincent. I think it kind of it agrees with the mental model I have of Vincent, and I agree with it so much that I kept it. So Vincent's personal favorite, but I think I would agree with that. His heuristic of research quality is surprisal, that we should aim to do work that is surprising. And I think this is, when I read papers, this is the thing that really makes me think that, oh, this is such a good paper, because I have a mental model of the research area that I'm working in. I have a mental model of the current state of the art, and then there's this one paper that completely breaks it. It's like, oh, like you can do this instead of whatever everyone else is doing, and that comes with the surprising factor. I think it also relates to being creative. I think most of the really creative work comes with this surprisal factor, and I think it's the same in the case of research as well. And then again, this is Vincent's theory of like what makes something surprising, but I agree with it. I actually changed the point here, so it's like both Vincent and mine now, or neither of us. So the main thing is people should gain a lot of information from it. The thing I was saying that like it kind of like breaks or updates my mental model. Now I think about the problem in a completely different way after reading the paper compared to before I had read it. So it should definitely be new. It should be understandable. So I can fit it, that's relates to the third point, I can fit it in the current paradigm and understand like what this work really does with respect to what exists. But it should also be a bit outside of the paradigm, in that it should not be that you read the paper, or the best papers are often not the papers where you read the first 2 lines and you're like, oh, that makes sense. They're often those that say that, oh, the current paradigm is broken in a certain way, and then you go ahead and you fix it. Here's an example of work from my research career that I feel is reasonably novel. I think all the works that I consider good from my set of research all share this kind of surprisal factor. And those are the papers that I would call have been the most novel. This is the same paper where you go from a single image of a scene to the 3D reconstruction, and you can sample from the distribution. We relied on something, a class of generative models that are called diffusion models, denoising diffusion models. Have you covered that in the class? Not yet. I think you will in a couple of lectures. But it works like any other generative model in that you start with some latent variables that are sampled from a noise distribution, from a Gaussian distribution. And once you're done with your generative process, you go to a sample from the actual manifold, actual distribution you're trying to model. So if you want to build a generative model of images, you take your data set of images, and at test time, you can sample from your latent variable, and you'll end up with images that look pretty much like the images that your data set kind of described. The manifold, it has learned the manifold of that distribution really well. The way these models are trained, so these are denoising models. What they do is that, let's say, during training, they slowly add noise to the training distribution. So they take, if you're building a generative model over images, you take any sample of an image, you add a bit of noise to it, and then the network learns to denoise it, right? And then what you add noise at different levels. If you add a lot of noise, you end up with the prior distribution. You added enough noise that there's no signal left. At test time, you start from complete noise distribution, and you slowly, iteratively denoise it, and you get to the real distribution. Just like super high level, without theory description of how diffusion models work. Did that make sense? Okay. So how do you train them then? You need samples from your actual distribution that you're trying to model. If you're building an image model, you have a data set of images, and you take samples from it, and you add noise to it. But that does not hold true in our case. We want to learn generative models over 3D data, but we do not actually have 3D data at training time. All we have is 2D data. We have images, we have videos, but we do not actually have 3D. So what do we add noise to, right? So we cannot really pre-compute 3D and add noise to it. We really want to do it from 2D. And this was the challenge we were working with. So for many months, I was trying to pre-compute 3D. It's obviously a wrong idea. What we needed was a way to actually sample 3D while never pre-computing 3D. And this, I saw this post on Twitter a couple of days back, which I think reflected my state of mind then really well. So people started, early days of 3D computer vision started with people training on 3D data sets. And then people like me, there were many people who went to like, oh, obviously there's not enough 3D data. You want to actually learn from images and videos. You want to learn self-supervised. You want to use 2D images. And then when it turned out that these models, like these kind of generative models work really well, people just abandoned that idea. And they were like, oh, let's go to 3D models again. You can just like take the 3D, you can add noise, you can denoise, it works really well. And that's kind of the dilemma that we were on. So like, how do you really, it kind of breaks the philosophy of like research, which I believed in. So how do you bridge that gap? And the way we ended up bridging that gap is by building a new class of denoising diffusion models, where you do not actually need to add noise to the quantity that you're trying to model, but you can actually add noise and denoise some observations. So in this case, you can add noise to 2D observations like images and videos, but the network internally learns how to sample 3D data. This is something which I think will be covered in future lectures, so I'm not going into more detail, but this is how it worked out. So just like identifying this kind of like core problem allowed us to build something that is surprising. And I think this was the novelty factor that I liked in this particular work. Another work I think that I consider to be novel, also because it was surprising, is this paper that we wrote. I think the reference is wrong. But in this case, you have GAN, a generative model, and you just take images from that distribution, and you just learn how to manipulate it. So in a generative model, you can take latent variables and you can sample images, right? But can you edit those samples? Can you actually play with the samples? Can you manipulate the latent manifold rather than just sampling from it? And in this case, it was just a ridiculously simple method that just like allowed you to click points and then move in the latent manifold. The training data is just images. You never actually see videos even, so you never know like how things deform, how things are supposed to deform. But with this very, very simple idea that we developed, you can actually now just go in the tool and start editing it. And in this case especially, the technical novelty, the actual techniques we built were not that novel, but just the theory of the problem, just the formulation of the problem was really novel that people had not considered. In this case, I think you can move the sun down. But yeah, so these are two examples from my research. I do not believe that these are the examples of the most novel research in the research area that I work in at all. I think there are much better examples. Two other ones I really like are Vincent's Siren paper. I don't know if you guys have read that. That was really, it came with a very surprising factor of like, oh, just like change the activation function and now you have all these nice properties in your neural network. That's why everyone liked it as well, because their mental models were updated after that. My advisor, Bill Freeman, he had this amazing work on motion magnification, where you could just take an image of something that is just completely still, like take an image of a bridge that is over a river, take a video of a bridge that is over a river, and he has these presentations where he would show you the actual video, and you would think it's an image because nothing moves, it's a bridge. But there's enough motion in that pretty static-looking video that you can extract how the bridge is actually vibrating. You can compute the frequencies. You can actually magnify the motion and watch the bridge move. And that was very surprising when I read it, that just to even start to believe that that information is actually there was surprising. And then the entire sort of toolkit that came with it also became really important. So it is like when you read papers the next time and you find papers that are really interesting, you think are really novel, maybe you can think back on what principles made you believe that these papers were really interesting, they were really nice, they were impactful, and so on. To come up with something novel, it is very important to understand what exists out there. So it is very hard to achieve novelty without knowing what has already been done. This is a visualization which I really like as well. I think this started from Philip. So this visualization is basically that you start with your high school. I think that's the innermost circle. This is the circle of knowledge. This is all the knowledge that exists in humanity. In your high school, you start with this innermost circle. That's the knowledge. Then you go to, that's elementary school. The next one is high school. And the next one is you do your undergrad. So that's why you get a bump, because you have a specialty now. You chose your major. After that, you do your master's, so you read research papers, and you end up at the edge of what people know. So that's like you read research paper that came out like last week or yesterday, and now you know exactly where the field is at. And then our job is to push the field. So there's the PhD. So you just like bump it a little bit, and you add to the information that the humanity knows, that the research problem, like no one else knew this kind of information, and you have added to it. That's the goal of research. This example, any guys on who came up with these slides? I think this one is easy. If you guys know who Philip Isola and who Vincent are and what they work on. No guesses? David? It is Philip. So this is an example of like Picasso came up with all this cubism and all these amazing forms of art, but if you look at what he was doing when he was 13 and 14, was like he was already a world expert on existing styles of art before he started exploring, and he came up with entirely new forms of art. So it's very important that you really master what already exists out there. It's not that you don't know or you don't have mastery over what exists. It's only when you have it, you can actually innovate and do things that people have not thought of. Okay. How do we do good research? This is a very common depiction of how to choose research problems. I don't know where it originated from, but I've been hearing this since I was an undergrad. Maybe you guys have also heard it. Is that there are two kinds of ways to find research problems. One is using a hammer, and the other is using a nail. Hammer is that you have a tool. You have developed something which is probably theoretical or something fundamental, and you want to find nails. Like, let's say, the people who build diffusion models. Like, okay, I have diffusion models. Now I want to run it on every nail. I want to model images. I want to model videos. I want to model sound. I want to model 3D. So you have the hammer, and you're just like looking for the right nails where you can have impact. The other kind of problem is you have the nail and you're looking for the hammer. So this is, I think, more, in my case, like it's like, oh, I want to solve 3D, that's the nail. And then I'm looking for the right hammer, like, oh, can I actually solve this using a diffusion model? Can I actually solve this using some other tool that just came out? Can I build new hammers that can actually hit this nail? I don't think there's like any, it's a lot of it is research based, a lot of it is like based on what you've actually developed or what other people have developed. But this is generally, I think, a true way of saying is like how we really think about finding a new research problem. And in terms of finding problems, you really have to find problems that can be solvable. And this is a good quote, which is good scientists study the most important problems they think they can solve. It is, after all, their professional business to solve problems and not to grapple with them. So you don't want to just pick something that is very ambitious. You have no ideas how to solve it. You want to find the most difficult problems that you think is solvable. You have the actual tools to target them. There's another, I remember there's, Richard Hamming gave a talk at Bell Labs, I believe. It's called You and Your Research. I might have a quote from it later on. And in there, he also talks about this. He says that, oh, at Bell Labs, people were doing all the interesting stuff, but the things that are the most fundamental problem, no one was working on time travel. Why was no one working on time travel at Bell Labs? Because we didn't know how to tackle time travel. So then you really go to the most difficult problems that you have the tools to target. And there are many different ways to contribute, of course. You can actually come up with a mathematical theory. You can prove some theorems which lead to this new class of problems, new class of methods. You can come up with empirical theory. You can figure out why things work the way they do. All the deep learning theory, I think a lot of it comes in this bucket. You really try to build empirical hypothesis and try to understand when that is true and when that is not for large systems. You can build tools. This tool helped me a lot in my early days of PhD. I don't know if any one of you has worked with it. PyTorch would be a better example now. So you can build tools that everyone else uses. You can propose entirely new problems. This was like a problem that completely looked at classification from a very different lens. You can solve old problems much better. So this is image classification. You can say that your deformable part models and everything else doesn't work. I'm going to go with a CNN, and that was a big thing. So you can solve old problems really well. And finally, you can also do communication. And this I've come to appreciate more and more lately, that you can actually present your ideas in such a nice way that makes it easier for other people to build up on the existing state of the art. This is probably the most important slide that if you have to take away anything from the lecture, I think you should take this away. I know Vincent and most of the other researchers that I talk to, they really stand by this, and I think for a very good reason. So these are the Heilmeier catechisms. So Heilmeier was a DARPA director, and you can go to the DARPA webpage, look for Heilmeier catechisms. There are 3 more which are missing from here, but I think these are the ones that are most relevant. And the task was like DARPA has to do things that are very high risk, high reward. But how do you evaluate what you should work on? How do you figure out like what are the risks, what are the rewards, what are the right problems to work on? So these are the catechisms that Heilmeier came with to understand which problems are worth looking into. So first thing is problem definition. What are you trying to do? And it extends further is like you should be able to explain the problem you're doing without using any technical jargon. So you should be able to really define what you're trying to do. The second thing you have to do is figure out and be able to explain how is it done right now and what are the limits of the current practice. Once you have that, what is your approach and why is it better? And you should be able to communicate this really well. In Vincent's lab meetings, this is something all his students have to do whenever they propose a new project. They have to come up with, like each slide, you have to be like, okay, what are you trying to do? How are people doing it right now? What is your approach? Why is it better? And the other point is also really important. Who cares? If you're successful, what difference will it make? You can start working on a very obscure problem that even if it's solved, it's like not clear at all if it will make any difference at all. So you should really think about why you're working on the problem. Does it will it actually make a difference in the research area or whatever end goal that you're interested in? And then the final point is, what are the midterm and final exams to check for success? If you define a project and you think that, it will take me 8 months until a deadline, or it will take me a year, how do you actually evaluate progress? How do you look at what you have to define? What are the intermediate results that you're looking for, and what are the final results that you will be looking for when you can say that this project has been successfully achieved? And this, I think, oftentimes when we think of projects, we're confused. We look at results and we're like, we don't know how it makes sense in terms of the project. Should we work on it? Should we not work on it? And I think falling back to this always helps. You can just look at it in this structured way and think about whether the problem you're solving is actually worth solving, or the project you're working on is actually worth working on. I'm not sure if this will also be required for your project presentations. Maybe it will be. Okay. I think now we've moved on to set of guidelines, or like things that generally help in research and in doing research and figuring out what to work on and things like that. So this is something which I think really distinguishes the great scientists from everyone else. So it is necessary but not sufficient to master the core knowledge in your field. You should acquire a unique skill set that helps you really advance the field. How do you do that? You can take difficult or unusual classes. You can read old papers. And this is an important thing because old ideas often resurface like decades after they have been lost. People have moved on to other ideas. Think of deep learning, or think of many, many other ideas that kind of were lost, and people just figured out that, now is the right moment to actually start working on them again. Maybe there's the right compute, maybe there's the right framework, maybe there's the right data now. So reading old papers is something which is very effective. And also reading papers, I don't think this is in the list, but like you should read papers in at least adjacent fields to what you are working on, but ideally also things that just interest you. Take on a complementary hobby. You never know what really inspires a new idea, or what really inspires you to come up with a new framework of thinking. And this is finally like talk to people in other fields. This is something I try to do in the beginning, where you want to attend talks when people are presenting talks, even though that might not directly be related to your research area, because often the innovations happen when ideas between two seemingly unrelated fields or projects integrate together to build a core framework that is like that gets you to another level of abstraction. This is a quote from John Hopfield, who came up with Hopfield networks. He was a physicist, and then he became interested in AI. And this is his quote: like, my answer to now what is, here's a research problem which is unusual, perhaps significant, novel, that I can pose and probably solve because of my background in physics. The situation would not be readily identified as a problem at all by those whose backgrounds seem much more relevant than my own. So because he was working on physics, and I think this is still very true. You often see physicists coming into AI and making really great contributions because they have this kind of background that often people who were studying AI from the beginning did not bother to catch up on. This is another quote. Do you want to guess who made this slide? It's a mix. I think everyone contributed to this one. So this is another quote which I found from an interview Alexey Afros did, I think day before yesterday. It came out on Quantum magazine. So Alexey Afros is one of the most creative and original researchers in computer vision and computer graphics. Pretty much every paper he writes is novel and very interesting and like amazing. And he had this quote, like, to be a good scientist, you need a secret superpower. You need to do something better than everybody else. The great thing about science is that we don't all have the same superpower. Maybe my superpower has been that because I don't see very well, I might have more insights into the vision problem. So his vision is not great. He can't drive. And in the video interview, so there's like text version, and then there's the video version. In the video version, he goes on to say that because his vision is not good, he doesn't see all the details. Because of that, he had the intuition that data probably plays a very big role. So he was one of the earliest people to start saying that if you want to really solve vision, you have to look at large data and not just look at geometric versions of geometric solutions, but just look at a particular image and try to reason about the image. You actually need to rely on data sets and memory in order to be able to solve it. And in this interview, he goes on to say that this might have been one reason that really inspired him to look into this direction, because he thought that his vision is not that great, and he must be relying on a lot of data and memory in order to perceive the world. So you never know. I think the takeaway is you never know what can inspire you. So the more breadth you have in your life, probably it is also good for coming up with innovative solutions to any problems that at first completely seem unrelated. The other thing I've been learning more and more about is that you should question obvious weirdness. And this is very easy when you're new in a field. So if you have just started working on a research area, when you read up the papers, when you try to build an understanding, you're often confronted with something that everyone accepts, but that strikes you as very weird. And that's because, like, if I've been working on this problem for 10 years, there might be something weird, but I've just internalized it. Like, that's how it is. Like, that's how I've been doing it. But for someone new, if they look into it, they'll be like, oh, that seems very odd. Why do you do it like that? And these are often very good research topics. And this is actually one of the reasons why oftentimes the biggest contributions in research areas are made by very young students who have just started working on the problem, who have just been introduced to the problem, and they just like kind of question the very underlying principles or just the very basic parts of the solutions that people have built. And as soon as you start questioning it, you can come up with like really interesting contributions. One of the examples from my research is another paper that we're presenting at NeurIPS with Vincent, and Cameron Smith was the first author here. In this case, the weirdness was like, why do we perform 3D reconstruction twice when we try to reconstruct a 3D scene in a neural manner, and when we do neural reconstruction? So I think you guys probably have talked about nerves, right? So in nerve, when you try and train nerve, you need the camera poses. Where do the camera poses come from? Well, the camera poses come from structure from motion, which is another 3D reconstruction method. So why do you need to first get this 3D reconstruction method that gives you the camera poses, already gives you the point clouds, the estimate of the 3D scene, and then you ignore the 3D scene, you take the camera poses, and you're like, oh, now I have a separate method that uses these camera poses, and now I'm going to again reconstruct the scene, but now in a nicer manner. So that kind of seems odd, right? Like, why do we have to do this twice? Does that seem odd? Would you agree? And so we developed this approach where you just don't do that. So you just have one method that you given an input video, it reconstructs the scene as well as the camera poses. So in this plot, you're seeing the camera trajectory, and in the other visualizations is the renderings from the 3D scene. And here you don't need to rely on any structure from motion method. You can actually use the same method to do both. Why was this difficult? Why could people not do this earlier? Well, once you realize that something is very odd, often the solution is not very complex. So the reason structure for motion can give you reliable camera poses, and the same is not possible with nerves, is because structure for motion relies on correspondences. It uses feature matching to come up with correspondences between images, and it uses those to solve for the camera poses, and that correspondence problem does not exist in nerve. So nerve doesn't actually use any correspondence information. In this case, we can add the correspondence information in a nerve-like framework. So you use optical flow. So optical flow gives you dense correspondences between frames. Once you start using those information, you actually don't need to rely on two different methods. You can actually solve both the problems of camera poses and of scene reconstruction in the same framework, right? And this is like, we're still working on this, and this is not just a cute thing that helps us avoid like running another script, but this is something that can be very, very practically useful. So when people run structure for motion, they have to wait for like GPU years on data sets to pre-process data sets. It fails often because it doesn't actually use the priors. It does it each scene independently. It's an algorithm from way back, like 2 decades back. And this makes it faster, it makes it robust because you're solving all of the latent variables jointly. There's another, can you guess who made this? I'm confused. I think it was Philip. We'll figure it out. So I am pretty sure this was Philip. You should always think about why you're working on the problem that you're working on. It relates back to the Heimler catechisms. What would happen if you were successful? Is this what you really want to happen? You should consider the impact of your work. And this is something I think that should be part of the framework when you're thinking about the Heimler catechisms. You should really write it down. Like, what do you think? Why do you really think you're working on this problem? Is it just because you had read about this other paper or other problem and you think that you can solve it just slightly better? Or is it because you actually think that that is something worthwhile your time and effort? This point is really important. So you should get comfortable being confused. I think it comes with any creative endeavor, but with research, I think it's very well formulated by Michael Black. And he says, there's an essential stage of confusion necessary for the formation of really new ideas. I call this the high temperature state where exploration happens. It can be uncomfortable for students and advisors, but I encourage it. And then he goes on, my role as an advisor is sometimes to raise the temperature, apparently increasing confusion by suggesting new directions. Then, at a critical point, I quench the system, dropping the temperature and helping the student close the deal. I wonder how his students would respond now when he tries to do that. Like they know his strategy. But I think this is something which good advisors often do, and for really good reasons. Again, in my last project, this was very evident. I was working on this generative model over 3D scenes for, I think, around 6 months. And I could make incremental improvements all the time. We were around maybe 80%. Like if like 100% is the results we would be satisfied with, we were around 80%. And I could just like add 1% every time. But we really needed this like really high confusion state, this high temperature state, which I think my advisors really helped in creating, where we just like completely abandoned that idea. Out of this like confusion state that existed for like maybe a month or two, in the end, the actual method just like looked completely different. Something came out which was very novel, which does not exist before. And often when you are the one working on the problems, you are the one implementing the solutions, you are the one actively thinking about it, it's very difficult to self-simulate this high temperature state because you always have an idea like, oh, this doesn't work, but maybe if I do this, it will work a bit better. It's often helpful to completely add confusion and think about radically new directions, whether those are the better ways rather than what you are actually doing right now incrementally. It also depends on which stage you are on. Like you should not do this when your paper deadline is in 2 weeks. But especially in the beginning and during the main development process, it's really, really important. And this is where this Richard Hamming's quote from this amazing, amazing talk that he gave, everyone should just read this transcript. This is the best, one of the best talks I've ever found out, I've ever read, which describes how to do great research. I think that's you and your research, and it really talks about a lot of things from your like personality to luck and how you actually do your day-to-day research, how that affects and what his theory is, like how it helps Shannon come up with the information theory. And he says that great scientists tolerate ambiguity really well. They believe the theory enough to go ahead. They doubt it enough to notice the errors and faults so that they can step forward and create the new replacement theory. If you believe too much, you will never notice the flaws. If you doubt too much, you won't get started. It requires a lovely balance. And I think he even has some anecdotal evidence where Darwin, when he had hypotheses for his theories, whenever he would see a negative result, he would make sure to write it down somewhere so that he doesn't forget and negate it or just like discount it. So every time you see some errors and faults, you really want to take note of that and think about whether there's completely a new replacement theory that should exist rather than the theory that you have right now. Yes?
What are your estimates for like negative results? Like oftentimes machine learning research, you just talk about it, like you have negative results and you want other
Yes. So first of all, I think negative results in terms of your research, it helps you a lot. And this is often a thing that advisors have to mention often. Even in like regular meetings and stuff, often students come and only with the positive results that, look, I had this idea and it seemed to work. Well, it worked only for 5% of the cases, but the student was like, this is good enough, I can make it work for the rest of the cases. So I think it's very important to keep track of all the negative results that you are having that really guides you to come up with the better theories. In terms of communicating it, I think most of the top conferences are not that open to simply negative results. So you can post them as workshop. I think there are many workshops that are open to those results, and I think I definitely appreciate those kind of results. There are a kind of negative results that are very useful and also appreciated at even the top venues, and those are the kind of negative results that kind of negate the entire approach to research that has been taken for less than 5 years. So there have been papers at CVPR that have taken like, here is an approach that people have been taking for the last 5 years to do 3D reconstruction. It turns out there is no learning, it's all doing nearest neighbor. And you can, or there are papers which say that, like papers have been comparing to all the previous works and have been reporting these benchmarks, and you always see the plots going up, the later papers are always better. Well, it turns out it was all the learning rate scheduling, and it was nothing about the contribution. And those things are really well appreciated. It really, those are novel. You create novel ways of evaluating and understanding the field, which is really important. If you have developed your own theory and that resulted in a negative result, I guess you have to just come up with a better theory. This slide is, first of all, this slide is so beautiful. Do you know who came up with it? Philip. Although the graphics might be from this source. But this is such the visualization of the colors is so nice. And I guess probably a lot of you would know. So the kind of work you want to do, you're putting in so much effort, so much time, so much stress in your life on this, these problems that you work on, and you want to make sure that those are the right problems. And I really like this definition of where you want to lie in terms of what work you do. There's the Ikigai concept. So you want to do work that you love, that the world needs, that you can be paid for, and the work that you're good at. And if you're missing any one of these, you get into one of these weird states. So let's look at it. This one is like you have all three, but you don't love it. So you're comfortable, but there's a feeling of emptiness. That one is everything is good, like you can be paid for it, the world needs it, you love it, but you're not good at it. Then there's excitement, but sense of uncertainty. It all makes sense. I think you really want to be you want to do work that really lies in the intersection of all these circles. And the other point, this is the point which is very difficult to actually put it in practice. So that's what I said. So like these are principles that I want to follow in order to do better research and go on to do better research than I have been doing. It's very, very difficult to see something that exists out there, but work on something that is unpopular. It feels almost wrong, but oftentimes this is the thing. If all the constraints are met, this is the thing that will very likely become popular if you do a good job. And this requires you to really think about the kind of problems you work on, introspect a lot, and have confidence and supportive mentors. If you actually find something that other people are ignoring right now, but it does fit all these constraints, then that's the best kind of work you can do. Omit needless bits. And this is also, I think everything here is like really important. It has probably been compressed over years of lectures that Philip and Vincent have given. So this is also not my slide. But this makes just so much sense. So perfection is finally attained not when there is no longer anything to add, but when there is no longer anything to take away. Most in the scientific process, when you're coming up with hypotheses to explain data, the hypotheses that end up having the most impact are the ones that are the simplest to explain. So using any observation in physics, like people come up with all these different kinds of theories, the theories that actually last, the theories that end up being influential are the theories that are the most generalizable. You cannot take anything away from that. That's the most core set of principles that can really explain some data. So really want to pick at your solutions, your methods, until there's nothing that you can take away which will not break the entire system. That's the kind of stable state that you want to be in. And that's where most of the understanding also happens. You really get to understand. Like, there's often papers where there's like a laundry list of like, oh, first you have to do this, then you have to do this, then you have to do this. Like, there's like 50 equations in the system, and you have no idea which one is actually important. If you delete one of them, is it actually still going to work? That you don't know. So that's the job you have to do when you're developing a method. And it's the same thing. It's like if you have the appropriate model. If you take anything away from it, you're going to have underfitting. But what you often see in actual research papers is overfitting. So that is a valid solution for fitting the data, but that's not the solution you actually want. That's not the hypothesis you want to create. You want the hypothesis space to be minimal, which can still sufficiently well explain the data. And I think this is, again, Philip, but I think it makes a lot of sense. So these are the number of terms in your loss function and the performance of your method. And I think any paper that has arbitrary number, more than 5 loss functions, you always see this. The number of terms in your loss function, you can keep increasing it, but the performance gain is going to be very, very, very minimal. You can see this ablative analysis in the papers where they remove one of the terms, and then you have to zoom in 10x to see that, oh, maybe it is maybe better. In some cases it doesn't, or you have tables where like it increases in the 3rd decimal point. But then you have the cost. So with every term that you have in your loss function, there's a cognitive cost for the reader, even for you to understand and explain your method to other people. There's a coding cost that increases with the number of terms in your loss function, the number of possible bugs that also increase, and what gets lost is the generality of the formulation. You didn't actually get to the core of the method. You didn't understand what is the core methodological thing that actually makes the problem work. And this metric is also something which I really like. I only figured out when I looked at the slides. I think this is also Philip. So the things you contribute in your research are the products, the discoveries, explanations, results, and tools that other people can use and build upon. But then you also give them costs. So the costs are words, equation, concepts that they have to go through in order to be able to take advantage of the products. So this metric makes, in my opinion, a lot of sense. You want to have as much product at the least cost. And this is kind of how the research world looks like. So you have the simplicity, so like how simple the method is, and novelty, how novel, how useful this method is. So if you have none, this gibberish. It's like, it's not simple, it's not novel. It's like, if you have a method that is very simple but not very novel, well, it's trivial. You can have complicated state-of-the-art systems. These are the systems that often beat benchmarks, especially established benchmarks. And you just have no idea how they beat the benchmark. There are like 50 things in the paper. You need the exact right hyperparameters that are required for training. You have no idea what actually helps. So it's like very not simple, but it actually performs really well. But these are the kind of contributions that don't generalize. If you move out of this problem and you want to take anything that this paper proposed to any other problem, you have no idea how to do that because you don't actually understand what actually made this thing work. It's very, very specific. What you want is to be in this simple and elegant point where your method is simple as well as novel. And at least you want to be on the other side of the curve. What does a reviewing system reward? It's not as correlated with what we just discussed. So the reviewing system often rewards the complicated state-of-the-art system because, and I think it is only because it's very difficult to reject these papers. So as a reviewer, when you look at these papers, they beat all the benchmarks. They have, like, in terms of results, the results are good, but it's not really generalizable, it's not simple. But there's like no reason to reject these papers, so they always get in. Simple and elegant almost always get in, but the more simple you have the method is, it becomes less likely that your method is going to be accepted because often simplicity is also taken for lack of methodical contributions, or like how much did you really add to the state of the art. but that's really a flaw of the reviewing system. Oftentimes, conferences have test of time awards, where 10 years later, they give award to a paper from 10 years prior at the same conference that has had the most impact in 10 years. 10 years, 20 years, I think, for CVPR it's 10 years. And if you look at those papers, they almost never correlate with the best paper awardees at any particular conference. The papers that end up having the most impact 10 years down the line are the ones that are really, really simple. And you'll often see this, like when these papers are given the award, they're always like, oh, the reviewers really didn't like our method. They said that it was not interesting, it was not novel. So this is just to say that like we should not overfit to how the reviewing system works, but we should we should fit to what stands the test of time, which is that we want to build systems that are simple and elegant. We want to build models, mental models of problems that can be updated. We want to build things that are really understandable and theories that are generalizable, that can be applied to other problems and insights that can be applied broadly. No questions so far, right? Okay. Also, if nothing makes sense, just like stop me. This is more in terms of scoping the contributions and writing papers. I think this is the only slide on writing papers. I believe there were more, but I didn't find them very interesting, so I just got rid of them. This one I agree with a lot, so that's why I kept this one. Whenever you write a paper and whenever you scope your problem, if you scope it too broadly, it's almost the case that it's indistinguishable from prior theory. And the other problem is that there's a lot of noise. Every time you increase the scope of the work, there's more noise. If there are 2,500 papers on NeurIPS, and if you just like pick a topic that is broad enough that half of the papers can come in that topic, it's very difficult to identify your paper and figure out what exactly that is that you did. And too narrow and you lose impact. There are not enough people who are interested in that thing. They're not going to read it. This happened to me, I think, early on, like in my FACE papers, where I thought they were very interesting ideas, but they were only read by people who were working on human faces. These ideas were very broadly applicable, but no one would read those papers to understand whether they're applicable or not. And we had to start working on the general problems for the community to understand that these are actually solutions that are worth looking into. So both sides are kind of wrong. You want to be right in the middle. So I think in this case, I think this is also Philip's side. So I think I'm hypothesizing what he was saying when he was presenting it, which is that if you have a generative model of images, you don't want to say it's a generative model which combines like all kinds of domain information. But if your results are a generative model of faces, then you probably don't want to pitch it very narrowly as just a method that is applicable for faces. And again, related to conferences and publishing venues and the noise, the vast majority of information at any academic conference is forgotten. And this is a good thing. I completely agree with this. So I don't think most people will even bother reading all the papers that are published at the top tier conferences, let alone the conferences that are not considered at the very top. And oftentimes you will read papers that are not published at the very top, but you will ignore papers that are at the top because of the kind of information that is gained from those papers. We tend to forget almost all but the simplest and starkest discoveries. And the claim of this slide, and this claim I think comes from this Moritz Hart from UC Berkeley. And I think I agree with it. We tend to forget all but the simplest and starkest discoveries. And this is kind of how, as humans, we move forward in the field. Complex and subtle discoveries are usually either overfit or unimportant. And we figure that out. And it's for a good reason that we ignore all these information that does not seem to be general enough, that does not seem to be important for us. This is the last slide that I have. I was working on the slides, and a lot of what is there in what I talked about, I think, is more on the level of like how do you figure out what you want to work on, and not a little bit on like how you should actually do the work, but not as much on how you should actually conduct your projects and measure your progress on a day-to-day basis. And for that, I just wanted to add this resource, which is really incredibly useful. This is my advisor Bill Freeman's resource on how to do research, and he really talks about like what do you do if you're stuck in your problem? You're just like not making any progress, and it has been a couple of weeks. He has suggestions on what you should do then, like how you should really present your work to mentors and to other people. What really distinguishes like really great students from students that are not making that such great advances. And I think this is a very, very useful resource. In other resources, again related to how you actually figure out what you want to work on and how do you actually develop a broad enough perspective of the problems that you're working on is, as I've very recently figured out, is by watching and attending debates. So in any research area, there are often contrasting views that researchers have. So in the case of vision, the two contrasting views are that, oh, maybe vision is pretty much all, or like most of vision is just discriminative. There's a feed-forward pass, and this is about like humans, not computer vision. So what do we do as humans? Like most of human visual processing is going to be just feed-forward processing. The images go in our retina. Output comes all the inferences that we make about the world. These models have neuroscientists compare the activations of these models to the activations in the human brain, the responses of neurons in the human brains, and they see remarkable similarity. And they're like, oh, of course this makes sense then, that this is how the brain works. And then there's the other view, which is kind of like what my research is closer to, is this generative view of like, oh, well, there might be a generative model in some form, and then the brain is actually doing inferences on these. But there are fewer tools on how to align these models with the inferences, the activations, and the responses in the human brain. But then they make other arguments on why they think that this is the way humans work. And I think a lot of this is supported with cognitive science, about thinking about and making experiments on human behavior, like how do humans really act, how do humans really make judgments, and then saying that, oh, if we build models that are kind of generative and do a generative inference, the models seem to behave in a very similar way that humans. So there is a very active and wild is like a strong word, but there's a very active and interesting debate on like which side of the which hypothesis is likely to be true. If there's a combination, how is that combined in the right way? Like, what does the brain really do? And there are people who do active debates on this. So this is, I think, a workshop proposal, and they did the document is really nice, and then they have talks where they kind of openly talk against each other in the debate. And I think these kind of debates are very useful in building a broader perspective of the research field and understanding the scope of a problem, where you are and what you think are the positive aspects, what you think are the negative aspects, and where do you think you can really make a dent in this field. And that is it. That's all that I could contribute. Thank you. Any other questions, remarks? Yes?
Are these slides going to ever be out?
I think so. Okay, sounds good. All right, if there are no other remarks, then we can end it here. Thank you.